Hello my dear, welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. So we already covered the entropy, okay? So study classes, previous classes, we already discussed that what is the entropy balance, how to entropy balance for the open system and for the closed system. And also we'll solved already one good question, that is when there is a plane slab and heat will transfer from that one phase to another phase, to what is the entropy generation for the bricks slab and what is the total entropy generation. So once you have to find the total entropy generation, please keep in mind that you have to take a immediate surrounding. What is the concept of immediate surrounding? The concept of immediate surrounding is that the effect of temperature gradient is appreciable. That means there must be a temperature gradient. So up to that range we have to select a imaginary boundary, that is your imaginary boundary, that is your extended system. So beta, in the extended system we have to already discuss that in the extended system, the system as well as surrounding. That means extended system you can call that isolated system, okay? Isolated system. So what is the so in the case of isolated system, the entropy generation is equal to change in entropy of the system total. Entropy generation, why? Because in that case there is a no heat transfer. There is a no heat transfer. Why? Because if you talk about the isolated system, that system there is no any energy interaction. Also there is no any mass interaction. So entropy transfer term is 0 in the sense of mass and heat. So what the left is there? The left is a generation. So that generation is the change in entropy of the system. And what is your system? System is isolated system. That means universe. So S generation is equal to, that means you can say that sir, S generation, the entropy generation, entropy production is equal to change in entropy of the isolated system, of the system. And what is the system? System may be, this is called isolated system, yeah, that is also called total. So in the case of where there the written is, where the this is the, where you have to see that entropy generation is equal to change in entropy of the system, that means that system is a extended system. That means this system is your extended system. Extended system. So my dear, see this one. If this is your system, so this is your extended system. This is your extended system. That means if heat will transfer from the system to the surrounding, that means its let's temperature, the system temperature is T, and T is the system temperature or system boundary temperature, and this is your surrounding temperature. And let's suppose T system is greater than T of surrounding. Let's suppose T of surrounding. In that sense, if you take a slope of this temperature drop, so from the surface of the boundary the temperature will continuously drop at that point of the immediate surrounding. After that the temperature profile will not affected, that means the variation of temperature is 0. That means this variation up to which range, that range you have to draw a boundary. That boundary is called immediate surrounding, and that immediate surrounding plus system, immediate surrounding plus system called extended system. Extended system. that is called extended system. So we have to apply the entropy balance for the extended system. When for the extended system, you always put the temperature, that is the surrounding temperature. If you find the temperature entropy of the system, you can put the temperature of the boundary. That means when we can put the temperature of boundary, if you want the temperature change of the system. When we put the temperature of the surrounding, if you want to the temperature total entropy generation. Total entropy generation, or if the entropy generation of the system, put the temperature is T, and if the total entropy generation, put the temperature surrounding. Okay, like that we can discuss. Okay, now so we have to this is the entropy balance for the open system. This is the entropy balance for the open system, already covered, and these are the special case of the entropy balance for the steady. That means the flow is steady. The flow is steady, single stream and adiabatic. The entropy generation is equal to M, and that is called a specific entropy. This is the specific entropy. When the property will multiply with the S, that property is the specific property. Okay. Now, so we have to solve this. We already solved this problem. That is the bricks, and there is a transfer of heat from this surface to this surface, and we have already determined the rate of entropy generation in the wall. That means what is the entropy generation in the wall? That means this is a internal entropy generation, and the rate of the total entropy generation. So in the case of total entropy generation, you have to put the temperature of the surrounding. That means if you find the temperature, that means entropy generation, one second, entropy generation okay, entropy generation, that means what is the entropy balance? Entropy in rate basis minus entropy exit plus entropy generation is equal to dSCV by dt. If many system, the steady system 0, that means steady device, that means the entropy generation S generation is equal to S exit minus S inlet. Okay. Now, if there is a heat transfer, only there is a heat transfer. So if you take like that, okay, beta. If you take like that, so there is a entropy generation. That means change in entropy delta S at inlet and exit. Okay, at inlet and exit. Now, so we can write like that, integration dq by T, that means this is change in entropy plus S generation is equal to delta S of system. If you talk about that means entropy in is entropy in the form of heat. There is no exit. If you take, there is no, only inlet is there. So this is the entropy generation. Now, my dear, this is the entropy generation. So in that case, see beta, in that case, if the system is steady, that is the steady. That means if the system is adiabatic, that means adiabatic, there is no heat transfer. Heat transfer is 0. System is reversible. That means S generation is 0. That means adiabatic plus reversible system is isentropic. Delta S is equal to 0. That means isentropic process. So reversible and adiabatic process must be isentropic, but the isentropic process need not be reversible. Adiabatic, why? Because it may be irreversible. So like that we have already calculated for that one. Now let's look at this problem. So we have to, today the motive classes is to only to solve the numerical problem, which is most expected question, or already there is a highly conceptual question. So let us see this one. Steam at that means this is your 7 megapascal, steam at 7 megapascal. Okay, this is the steam and at a 7 megapascal, and the steam is 450 degrees centigrade, is throttled. See my dear, there is a throttling device. What is the throttling? We already covered that. Throttling, that means unstrained expansion. Throttling, that means unstrained expansion. That means there must be expansion. Expansion, that means it's reduce the pressure. That means in this case it will reduce the pressure. Okay, there must be a throttling process is expansion process. Throttling is unstrained expansion. So in this case the pressure will reduce. So see this one, 7 megapascal stream in enter and exit is 3 megapascal. Exit is 3 megapascal. Okay, the exit is 3 megapascal. So there must be expansion. So throttling, there must be expansion takes place. Expansion. Okay, that means expansion after throttling, exit is less than the inlet to the throttling. So there is the inlet. And what is the one special feature of the throttling? Throttling is approximately isenthalpy process. That means HI is approximately HE. It is not like that throughout. It is not exactly we can say that this is the isenthalpy process, but the throttling before and throttling after, the enthalpy is same. It is not necessary that enthalpy will throughout the same from inlet to exit. From inlet to exit. So we cannot say the throttling must be isenthalpy process. It is not. It can be. It can be. It cannot be. Okay, depending upon the fluid. Okay. Now, in the valve to a pressure, this one during the steady flow process. That means there is no any property change within the system with respect to time. Determine the entropy generated. Entropy generation during this process. Now, my dear, why the entropy will generated during this process? Why the entropy will generate during this process? First question. The entropy generation due to unstrained expansion. Unstrained expansion. That means irreversible process. Due to the irreversibility, the entropy must be generated. And check the increase of entropy principle is satisfied or not. Also will check the increase of entropy principle. That means what is the increase of entropy principle? Change in entropy of the isolated S generation of the universe must be greater than equal to 0. That means we have to also prove that S generation is greater than 0. This is the principle of increase of entropy for the irreversible process. For the irreversible process. Now, the condition it is given, state first before throttling, state second after throttling. It is given. The state it is given. That means initially what is that? Initial pressure. So see this one, state first. This is the state first. State first, and we state first the pressure it is given, temperature it is given. Go to the steam table. So from the steam table, this value you have to taken from the steam table. So this is steam table. So from the steam table we have to find the enthalpy and specific entropy. Specific enthalpy and this is specific entropy. Why? Because for the vapor, for the gas, we have to required a two minimum property. We have required minimum two property to identify the state. So minimum two property we have, if we have, that means pressure and temperature we have, we can easily find the other property. Okay. Now after throttling, we know that the pressure, this is a state number 2. So how to find state 2? We know that pressure P2, this is very important. We know that pressure P2 3 megapascal. How to find the third property so that we can identify other property? So in this, according to this, we know that the after throttling the enthalpy is same. So H1, so this P2 and this H1 at this H1. Why? Because H1 equal to H2. So we have P2, we have H1. We have P2, we have H1. Why we at state 2? Why we take H2? Why? Because why we take H1? Why? Because H1 equal to H2. Isenthalpy. That means inlet and exit are same. So in this manner, we have to identify the two property, pressure and enthalpy. First, we have to identify pressure and temperature. Mind it. First, we have to identify pressure and temperature. Accordingly, we have to identify the other property. Second, we have to identify the pressure and enthalpy. What is the concept of enthalpy? That means throttling process is isenthalpy process. So H2. So accordingly, we have to find entropy 2. That means specific entropy at point 2. Once we have to identify, we can easily find out. No problem. Okay. So see, this is your throttling valve. So this is a throttling valve. That means this is throttling. This is a throttling. Throttling, that means you can reduce the area of the passage. That means you are you enclose. That means this is your valve, which try to reduce the area of this passage. We try to reduce the area of this passage. There is an inlet section. This is your, if you take throttling valve as a control volume. If you take valve as a control volume, that means this is our control volume. This is our control volume, okay? Valve as a control volume. So if we reduce the area of that passages, if we reduce the area of the passages, pressure will be decreased. So see this one, initially inlet, this is the fluid in. So this is your in, and this is your exit, okay? So fluid in at pressure P1 and temperature T1. So, and pressure P2 and exit is H2, and that H2 is equal to H1. So from this table, we already know the value of enthalpy H1. Okay? Hi Atul. So if you draw the TS diagram, we locate the, this is generally superheated steam. This is generally superheated steam. So this is the saturation curve. What is the red line denote? Saturation curve. And there is a critical point is there. No problem. This detail already will cover in the detail class. So this is your critical point, okay? This is your critical point. So this is your critical point. This is your critical point, okay? This is your critical point where the saturated liquid and saturated vapor are meets, okay? No, not. You are right. Very right question. Atul, this is very right question. Many students get confused here. See this one, it is, you are right, throttling, it is not necessary. It is not necessary. It is not necessary. That means if you are asking the question like that, ki, sir, for throttling enthalpy always remains constant, the answer is absolutely no. Or you can say that no sir, it may not. It may not. The answer is it may not. Why? Because the throttling, this is the inlet. This is the inlet and this is your exit. So at inlet or exit enthalpy is same. At inlet and exit the enthalpy is same. But it is not necessary that enthalpy is throughout same from inlet to exit. Inlet exit is the cross section area. It is not a state point. It is the inlet cross section. It is the exit cross section. That means at this cross section, just inlet to the throttling valve, the enthalpy is same throughout the cross section. That means at any cross section, if you take at this cross section, if you take any location, the enthalpy is H1 and exit enthalpy is H2, and that enthalpy are same. It is not necessary that through I to E enthalpy is constant. It is not necessary. So it may not, it cannot be said that, matlab you cannot say that, that means we cannot say that, it is isenthalpy process. Isenthalpy process. It is not necessary. But it's depend upon the fluid also, beta. Such type of fluid that enthalpy will remain throughout the throttling, the enthalpy is same. It may be. You can read in the refrigeration. So refrigeration is the some kind of the fluid in which the enthalpy throughout the same. See my dear, what is the meaning of that one? If there is an ideal gas, so we can take that CPTI is equal to CPTE. So CP will cancel. So TI is equal to T exit. That means you cannot say that if there is an ideal gas, the ideal gas is an isothermal process. During the process it may be also, yeah, right. During the process it will change. That means what is the process during the process? That means the enthalpy at inlet section, you have H1, H2, H3, H4, H5. And you find the enthalpy at exit, that means H1 dash, H2 dash, H3 dash, H4 dash. Now if you equate H1 with respect to H1 dash, these are same. H2 with respect to H2 dash, these are same. H3 with respect to H3 dash, these are same. But it is not necessary throughout 1 to 2 are same. Yeah, I to E are same. But there is some refrigerant also in which the enthalpy is same. So if there is an ideal gas, we'll confirm with this concept. If there is an ideal gas, it is flowing. So in temperature at the inlet is the same as the temperature at exit. Except ideal gas, you cannot say. That means after the throttling, the temperature may be increased and temperature may be decreased. But if you throttle the ideal gas, temperature at inlet is temperature is exit. That means it is not necessary that is an ideal process. It is not necessarily that these are isothermal process. Okay. Why? Because we cannot say that this is the isenthalpy process. Okay. So we have to state first. So state first from your superheated table, steam table, you can identify 450. So accordingly, this is the isenthalpy curve H1. So accordingly, you have to find S1. Okay. Now there is a pressure will drop. So pressure will drop, temperature will drop. So temperature will drop, but the isenthalpy process. So at H2, so H2, you have S2. As H2, you have, this is T1, this is T2. So at T2, you corresponding to S2. So this is your delta S. That means this is your delta S, specific entropy. Okay. So this is your delta S. So the process 1 to 2, there is a throttling process. This is your throttling process. And that is called, see beta, this is constant. Why we take a constant? It is not look like a constant. It will says that means H1 is equal to H2. So it is not a constant. H is, we cannot say this is a constant. H1 equal to H2. Only we have to find the property at point 2 with the help of H1. So we have to require two property. So one property is the temperature we have, the pressure we have, and other property how to find, we have to take the same enthalpy as H1. So from that one you identify the H2. So from that one you have to S1 and S2. So how to find the entropy change? So beta, to find entropy generation, please see. To find entropy generation, to find S generation, okay, dot, you can write like that. Rate of entropy generation during the process, during the process, okay, we have to find it. Now, what is the inside between the inside of this one? The inside of this one, it is a steady flow, okay, steady flow. What is the physical meaning of the steady flow? That means change in mass of a control volume is equal to 0. Change in mass with respect to time, change in energy within the control volume is equal to 0. Change in entropy, all the property is equal to 0. So this is the condition for the steady flow. This is the condition for the steady flow. Now, and the throttling, there must be these are two very fundamental assumptions. There is no any working device, so work transfer is equal to 0. Why? Because there is no any working device, there is no any installation of fan like that, electrical heater, no anything, so no work transfer, and we can assume the throttling is an adiabatic process, so there is no heat transfer. So my dear, adiabatic, if there is a reversible, so in that sense isentropic. This is isentropic. If adiabatic is irreversible, that is no, entropy must be increased. That means delta S must be greater than 0. Delta S must be greater than 0. So there is, we cannot assume this is an open system. That means this is your valve. This is your valve is there. This is your in here. and this will exit here. So there is a mass in, mass flow rate steady, so there is a mass flow rate out. But there is a no energy transfer. So there is a energy transfer. Why? Because entropy change, the responsible factor of the change in entropy is heat and mass. So there is a no any heat transfer. There is a no any heat transfer. There is a no any energy transfer. Why? Because we assume that this throttling device is fully adiabatic. This throttling device is fully adiabatic. Okay. Now there is a mass in, that means one inlet, one exit, single stream. There is a single stream, one inlet, one exit. Okay. So what is the entropy generation? Just now we see that if you balance the entropy, S in dot minus S exit dot plus S generation dot is equal to d S CV by dt, and we know that this is 0 for the steady flow. This is 0 for the steady flow, and there is inlet and exit is due to the mass. Inlet and exit is due to the mass. So if we multiply with m dot, so there is a S inlet minus m dot, there is a S exit plus S generation dot. So what is the entropy generation? S generation dot is equal to m dot S exit minus S inlet. Yes or not? What is the mass flow rate? Is it given or not? So this will ask in the entropy generation. This will ask determine the entropy generation. So we have to find the entropy generation kilojoule per kg. Why? Because mass is not given. So just you have to divide it. That means S generation dot divided by m dot is equal to S exit minus S inlet. So this is what specific entropy generation. That means this is a small sg per unit mass. So this is not a specific, this is a per unit mass basis. So what is the exit entropy? We have already know what is the exit entropy. The exit entropy is 7.046 per kg specific, 7.0046, 7.0046, 7.0046 minus what is inlet? What is inlet? 6.6353, 6.6353, 6.6353, 6.6353. If you subtract this one, how much it is? If you subtract this one, this is 0.696.3, 0.37 lagbhag 7 kilojoule per kg. See my dear, that means the S generation, that means S generation dot is equal to 0.37 kilojoule per kg Kelvin. Now my dear, so this is a S entropy generation, and that generation is greater than 0. So it satisfied the principle of increase of entropy. It satisfied the principle of increase of entropy. That means entropy always generation. Now beta, what is the cause of this generation? What is the cause of this generation? First tell me, why the entropy will generate? You can say that there is irreversibility. What is the cause of irreversibility? So entropy generation is due to irreversibility, due to highly irreversible process. Highly irreversible process. Now someone says that, sir, why this is highly irreversible? See, I am asking you a question. Why the entropy will generated? The entropy is generation due to the highly irreversible. Why this is happening? Why this is highly irreversible? The second question. Why this is highly irreversible? Why? Because the pressure is decreasing, sudden decreasing. You reduce the area of the wall. If you reduce the area of wall, the exit section, the pressure will very lower. That means this is your approximately, that means why? Because why? The question is why? 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 Because P exit is less than P inlet, that means the expansion will take place. That means expansion of the fluid, expansion of the fluid, expansion of the fluid due to unrestrained, expansion of the fluid due to unrestrained expansion. So beta, unrestrained expansion is a kind of expansion in which the entropy always, that means the entropy generation, yeah, total entropy of the system always increase. This generation is also called delta S of the system. Delta S of the system. Okay. So this is your entropy generation. This is your entropy generation. So this is the throttling process in that. So this will generate the entropy during the process, and that generation is due to unrestrained expansion. Why this is? Why? Because unrestrained expansion. So I hope you now you understand the concept of what is the concept is there. Okay. So this is the one of the best example of the throttling process. Now we will see this question next. So this is your next question. It is visible? Yes, it is visible. Okay. What is this question? See this one. This is the next example. What is that? Please read the question carefully. Read the question carefully, beta. See, what is that? There is a lake. All the terms have a meaning. It is not a beautification. There is a lake. Lake is there. Okay. So in the lake, it is like a lake. That means a thermal reservoir. So there is a lake, and lake have a temperature. That means this is a thermal reservoir. There is a lake, atmospheric air, ocean, room air. When there is a computer as a system, so room air as a system is a thermal reservoir. So these are all are act as a thermal reservoir. We will just discussing you. So lake, and this lake at a temperature 285 Kelvin. Okay, the lake have a temperature 285 Kelvin. Now a 50 kg block. So there is a iron block. You know that there is an iron block. How much the mass? 50 kg of iron block. At what temperature? 500 Kelvin. So the temperature of the block is higher than the temperature of the lake, much higher than. Thrown into the large lake. There is a large lake. That means what is the meaning of large lake? The large lake is the meaning of this meanings, that means thermal reservoir. Thermal reservoir. Okay. That is at a temperature 285. How much it is temperature? 285. The iron block eventually reach. This is very important. Eventually reach. Why? Because it is a quenching process. Eventually reach the thermal equilibrium. Thermal equilibrium with the lake water. That means after some time the lake water and the cast iron, that means iron block, have a same temperature. That means delta T tends to 0. Thermal equilibrium, that means the change in the temperature. Delta T tends to very negligible, tends to less than 0. That means the temperature difference after some time, eventually after a few seconds, the temperature of the block and temperature of the lake water are same. Okay. Now, assuming a specific heat of the iron, this is the iron specific heat given. Why? Because specific heat of the solid at a constant pressure and equal to the constant volume is equal to a specific heat of the iron. So solid. So this specific heat of the solid, it is given how much? 0.45 kilojoule per kg Kelvin. Now what you have to determine? You have to determine number A, entropy change of the iron block. So first we have to find the entropy change of the iron. Second, entropy change of the lake water, that means a reservoir. And third, entropy generated during the process. This is one of the best example I am telling. Very classical example. Very classical example. Okay. So this is your lake. Now, what is there, beta? We have to solve. So this is your let's suppose this is your iron block. This is your iron. Okay. This is your iron. And this iron are placed in a thermal reservoir. This is your lake, dipped into a lake. Now you think what happening during this one? What happened during this one? Why? Because this lake have a temperature. How much temperature of the lake? How much the temperature of the lake, beta? This temperature of the lake is 285 Kelvin. What is the temperature of iron block? 500. Okay. This is given. Now obviously, beta, now obviously if it will dipped into the water, there must be a heat transfer. Yes or not? There must be a heat transfer. That means that heat will transfer from the block to the lake. From the block to the lake. Q dot. This heat will transfer. During the transfer of heat, after some time, it reaches the thermal equilibrium. Now, my dear, so there are two systems. One is the lake. One is the lake. One is the lake. Other is the iron. Third one is the lake plus iron. Plus iron. Just think. Just think. First, there is a lake, there is a iron, and there is a lake plus iron. Okay. We have to think like that. Okay. So lake behave as an thermal reservoir. Why? Because there is a large thermal reservoir. Act as a surrounding. This is your surrounding. And if this is your thermal reservoir, then the temperature of the lake is fixed. It is not changed. It is not changed. That means if the heat will reject to the iron block, the temperature of the lake doesn't change. That means the temperature of the lake is fixed. How much? 285 Kelvin. Now, so my dear, what is the final temperature of the iron block? If this temperature doesn't change, so what is the temperature of the iron block? Obviously, it is when it is equilibrium, when the iron block reach at 285 degree. So iron, it is act as a system. We have to take iron block as a system, and this iron block system have initial temperature T1 is equal to 500 Kelvin, and after thermal equilibrium it's attained a final temperature 285 Kelvin. It is right. It is right. It is right. So if it is not a lake, it is something, there is a aquarium like that. So we have to find the energy balance. Due to that energy balance, we have to find the final equilibrium temperature. That means what is the energy will out, the same energy will take, and accordingly we have to find the temperature, final equilibrium temperature. But by default here the lake act as a thermal reservoir, so lake temperature doesn't change. So what is the final temperature of the iron? It is the equal to the lake temperature. So this is okay. Now lake plus iron, it is act as a isolated system. Isolated system, and we know that delta S of isolated system is equal to delta S of lake plus delta S of iron, system plus surrounding. So if you find the entropy change of the lake and if you find the entropy change of the iron, if you add, that is called total entropy, the entropy generation during this process, the entropy generation. So this is your also called entropy generation, S generation during the process. What is that? Delta S of lake plus delta S of iron. So we have to find the entropy generation. Now first we have to find the entropy, that means entropy change of iron and entropy change of the lake water. First we have to find, then we have to add. So first we have to find that entropy change of iron. So iron entropy change, so it is temperature change T initial, so iron have a temperature T initial and final have a T2. So what is the entropy change? Mass it is given. So what is the entropy change of iron? Delta S of iron is what? M C ln, we have to T2 by T1. We can easily find for the iron. Why? Because these have a constant volume. So if you write the iron, that means if you write like that, MCV, yeah, you can also write like that, sir, delta S is equal to dQ by T, and what is dQ by T? MC dt by MC dt by T. So what is the change in entropy? Delta S is equal to MC ln T2 by T1. T2 by T1, or we can also know that this is also knows that, and or we can also know that delta S of the system is equal to mCV ln T2 by T1 plus R ln V2 by V1. We know that this thing already derived. So for the iron block, it is an incompressible substance. So change in volume is 1. So this is 0. So 0 mCV, and CV for the iron is same as the Cp. That means C of iron. So put the value of mass of the iron is given. C it is given ln T2 by T1. So how much the delta S of the iron? This delta S of the iron is equal to mC of the iron, mass of the iron, C of the iron, ln T2 by T1. Put all this value, beta. What is the mass of the iron? 50 or 5 kg. What is the C? C is 0.45. ln, what is T? Always put in Kelvin. 285 initially and finally 300. So what is this one? See this, my friend, minus 12.65 kilojoule per kg. See this one. That means the entropy change of the system. That means if you take, this is your iron block. So if you take iron as a system, so this system entropy will reduce. Why system entropy will reduce? Why system entropy will reduce? Why? Because there is must be heat transfer from the system to the surrounding. So if heat will out from the system, this Q out, and this Q out is negative for this iron. So this is negative. That means if heat will reject from that system, if heat will reject from this system, that is called, that in that sense the entropy will reduce. Entropy will reduce. So in this case the entropy will reduce. So there is a must be reduction in entropy of the iron block. Now how to find the change in entropy of the lake? So delta S of the lake, and lake act as a reservoir. That means this is your reservoir of the lake, and it's take a heat. It's take a heat. Okay, it's take a heat. So, but its temperature is constant. Its temperature is constant. So, at a constant temperature, if there is a heat will receive or reject, that is called latent heat. That means this heat from the iron, if heat will supply, that is called sensible heat. But if the heat will taken by the lake, that is your latent heat. Why? Because we take, so heat will receive from the iron is your sensible heat, and heat will taken by the lake, it is a latent heat. Why? Because the temperature is constant. So what is that? This Q divided by T of lake. Okay, why? Because lake is our system boundary. So what now what amount of Q we don't have. So how to find Q? First we have to find Q. Apply first law of thermodynamics of TD. What is that, beta? First law of TD for iron. Okay. So Q is equal to delta U plus W. Yes or not? So what is Q? You have to find it. Q. So there is no any work transfer. There is 0. Delta U, mass of the iron, C into T2 minus T1. So what is the mass? 5. What is the C? 0.45. What is T2? 285 minus what is T1? 300. So how much is this, beta? How much it is? Please, it is your 4838. So minus 4838 kilojoule. See, my dear, this is minus. Why minus? Why? Because we have to find the heat with respect to iron as a system. We have to find the heat transfer with respect to iron as a system, and from the iron heat will out, so it is negative. Now, but if you take a system as in the form of lake, so heat will in, so instead of negative will be positive, plus 4838 divided by what is the boundary temperature of 285. 285. What is this answer? This answer is 16.97. This was 16.97 kilojoule per Kelvin. So this is lake. Now you have to find the, now there is, you have to find the entropy generation during the process. If you find that entropy generation during the process, or it may be asked like that, the total entropy change of the process. Total entropy change, total entropy generated, to the entropy generation during the process. See, these are the same question. This C have a same type question. How it will ask like that. See, this is C number. C is the entropy generation during the process, or the C will ask total entropy generation. Yeah, they are asking like that, total entropy change. So they are the same question I am telling you. Many students get confused here. So total entropy change or total entropy generation or the entropy generated during the process, these all are the same question. So how to find? We know that, beta, we know that this is our iron block. This is our iron block, okay? This is our iron, and we take iron as a system. We take iron as a system. Now there is a lake, and lake as a surrounding. Lake as a surrounding, and we have to take total as a system. So this is your isolated system, yes or not? This is your isolated system, yes or not, please? Isolated system. That means, what is the exchange of this one? This is only possible from this one to this one. But the exchange from the outside to inside is not possible. Not possible. So this is an isolated system. And we know that S generation is equal to delta. Why? Because we know that. What is we know that, beta? S in, if you find S in minus S exit plus S generation is equal to delta S of the system. Okay. Now, there is no any S or in. Why? Because there is an isolated system. So, this is 0. Why this is 0? Why? Because isolated system. Isolated system. And this system is what? Isolated. Isolated or total. Or total. That means the S generation is equal to change in entropy of total. So this S generation, and what is the total entropy? Summation of all entropy for the system plus summation of entropy for the, if you may write like that, delta S for the iron plus delta S of lake. So we have delta S of iron, how much? Delta S of the iron minus 12.65 plus delta S of surrounding lake is 16.97. So if you solve this one, this is your 4.32 kilojoule per Kelvin. This is the entropy generation. Okay, this is your entropy generation. You can find this other way also. This equation is applicable for this. We are considering the isolated system. Now, entropy generation during this process, another method. What is the another method? Other method. You have to find this method also. Let's see, this is your iron block, okay? This is your iron block, okay? And from the iron, there is a heat will transfer. Yes or not? Q out. Q out, okay? So, and we take this iron block as a system. This iron block as a system. System is only iron. Only iron. Now, we have to apply the entropy balance. S in minus S exit plus S generation is equal to delta S of iron. Yes or not? So, there is no any S in, only S exit is there. Yes or not? There is no any S in, only exit is there. So, exit is what? Minus Q out. And what is the system boundary temperature? This system boundary temperature T. And T is what we have to see, my dear. This is a very important, I am telling you. What is the system boundary temperature? Now, my dear, if we take, see, the iron continuously changing its temperature. Iron temperature continuously it will decrease. Which temperature you have to take? This, now this time you have to take, so this is your not, this is your for the system, you have to take the system, it is not iron, it is immediate surrounding concept is there. That means what is the iron temperature that will affect little bit further. So this is your this is system, so this is system, and a system is equal to is a extended system concept, extended system. Why? Because beta, see my dear, this is your iron, okay, and iron have a temperature T, iron have a temperature T. Let's suppose this is your immediate surrounding, this is your immediate surrounding, and its iron temperature, and what is the temperature profile in this one? Let's, this one, this is your, so this is the temperature of iron and this is the temperature of surrounding, it will drop like that. After that this is constant, after that this is constant. So after that this is constant, that means during this process, during this one, the temperature will change. So this is act as an immediate surrounding, immediate surrounding. So in that case, what is the temperature? Temperature of this boundary, T of this surrounding, this surrounding. And what is the temperature of this surrounding? This is your T is equal to 285 Kelvin. This, that means this is your lake temperature. So put here T lake. Very important, I'm telling you. Very important, I'm telling you. This is very important, okay? T of lake plus S generation, okay, plus S generation, and that S generation is equal to, and now this is not iron, this is an extended system. So delta S of extended system. So what is the S generation? Q out divided by T of lake plus delta S of extended system, okay, okay. And what is that extended system? What is the system? System is only iron, that means extended system. So this is extended system, you have to lake, so this is extended system, and the extended system, that system is this one, na? This one. So there is a iron very nearer to this one. So what is out? Out is 4831, 4838. What is the temperature of the lake? 285 plus what is the temperature of this system? Minus 12.65. So if you calculate this one, these are the same answer, 4.32, 4.32 kilojoule per. This is the beauty. So you can solve in this manner also. You can solve this question in this manner also, okay. So this is the beauty of this question, ki how to tackle that one and how to draw. So the in the extended system, though the temperature of the boundary, but the system is iron only. Iron. Don't confuse. Why? Because we have to take a system as iron, but little bit farther. Why? Because this is very nearer. Very, that means immediate surrounding. It is not a surrounding, it is a immediate surrounding. So this is your immediate surrounding, this much. This is your immediate surrounding, this is your immediate surrounding, this is your immediate surrounding. So I hope this question is clear now. If you have any problem at anywhere, just comment this video lecture, and what is the problem you have to face, just comment on your chat box. So this video is available for the long time of that one. So please studies, and if you want to learn some similar question, yeah, some highly concept question, you may also comment on the YouTube. Okay, so there is a very so in this question they have a two method. Which method you have to best, which method you have to like, that will also comment. Okay, thank you, bye bye.